All right, hello everybody. Welcome to the 6th lesson of Unit 2, which is on resonance and formal charge. Today our learning objective is to be able to draw Lewis structures that show resonance and use formal charges to decide between possible structures. So today's essential knowledge is that resonance must be shown when multiple Lewis structures are possible for the same molecule. The octet rule and formal charges help determine the best structure, and Lewis structures have limits, especially when there is an odd number of valence electrons. So when we draw Lewis dot structures, we're really just creating a model that shows how atoms connect, where the bonds are, and where the valence electrons go. But to truly understand Lewis structures, we need to look at how electrons can behave in molecules, specifically whether they're localized or delocalized. So localized electrons are stuck in one place. They're either in a lone pair or on a single atom or in a bond between two atoms. Think of them as like home bodies, and they stay in that one spot and they don't move around. Whereas delocalized electrons, on the other hand, are more like travelers. They don't belong to just one atom or one bond. Instead, they spread out over multiple atoms. And this is why molecules with delocalized electrons have resonance structures and are more stable and can even conduct electricity better. So when you see resonance in a molecule, it's basically showing us that electrons aren't locked into one spot. Instead, they're shared across different bonding locations. And that gives us a much more accurate picture of how a molecule actually behaves. Now let's look at how we can actually spot delocalized electrons. So the trick is simple. If we are comparing two resonance forms of the same molecule, if you can see a pair of electrons that shows up in one place in one structure, but a different place in another structure, that pair must be delocalized because it can bounce between those two atoms. In other words, the electrons don't belong to just one atom, they are spread out. So let's look at ozone, the example in the yellow box there. Notice in these two resonance structures, one oxygen has a double bond in the first structure, but in the second structure, the double bond has shifted to the other oxygen. The same thing happens with the charges. They move positions between the resonance form. These shifting tells us the bond and the charge are not locked into one spot. Instead, they're delocalized across the molecule. And that's why the real structure of ozone isn't just one single drawing, it's a blend of both of those drawings. So our resonance structure for ozone would look something like this, where we have the sigma bond for both of the oxygen to oxygen bonds. However, that dotted line there is showing you that at any point in time, if you froze the molecule, a double bond could be there, but it's really sharing between both of them. What I want to go over to is if we're talking about a single bond between two oxygens, the actual distance between those two oxygens would be 148 picometers. Now, if we had a double bond between two oxygens, that would be 121 picometers. So you can see that if we were to freeze it in time, sure, the double bond would be shorter than the single bond. However, that's not actually how it exists. Since it's constantly bouncing back and forth, they end up meeting somewhere in the middle. And in the actual molecule, you will have a length of both of these at 128 picometers, which I know I just wrote in black. Let me rewrite it in yellow for you. So when you have a resonance structure, the length of all of the bonds that has that delocalized electrons, they're all the same length. So let's do that same thing with the carbonate ion. So with this polyatomic ion, we have carbon at the center. We have 3 oxygen atoms. And the way that I draw these is I go ahead and bond out all of the electrons from the central atom just because I know it's going to give me a 0 formal charge. So since carbon has 4 valence electrons, I know it's going to bond out 4 times. So if I put a single bond on each oxygen and then just double up one of the bonds, That means carbon now has its 4 bonds. And then I add all of my lone pairs to the oxygen in order to get each oxygen at a full octet, or 8 electrons. Now looking at these, I can always double check my work, right? I know carbon has 4 valence electrons, and then oxygen has 6. And then I have a -2 charge, which means I also have an added 2 electrons to my total valence electrons in the molecule. So I should have a total of 24 valence electrons. And if I look at the molecule I have now, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So this would be a correct molecule. Now I just have to assign my formal charges. So remember, when we're talking about formal charge, we went over in class that if it's bonding how it is not supposed to, you should calculate formal charge. Now we know an oxygen atom has 6 valence electrons, so when you did the Lewis dot structure, it clearly shows that it should have 2 lone pairs and form 2 bonds. Well, these 2 single bonded oxygens are not pairing that way, so we should calculate formal charge. We know formal charge is the number of valence electrons minus the dots minus the lines. So we have 6 minus 6 minus 1 gives us a -1 on each one of these oxygens. Now, this brings us back to resonance. Now remember, resonance is the delocalized electrons being shared between all of the possible bonds. And that is going to be this pi bond here between the oxygen and the carbon. That is going to be your delocalized electrons that are going to be bouncing between each of the oxygens. And that would just look like moving that double bond to all of the oxygens on this polyatomic ion. So now that we have our 3 resonance structures, now we want to form our resonance hybrid. Remember, you're just going to draw essentially the skeleton structure of it, so our carbon and our 3 oxygens. And then we know each carbon to oxygen bond has a sigma bond that will stay and are localized. And then we're going to show the delocalized electrons as a dashed line. Now let's do the resonance structure for nitrate. So first let's add up all of our valence electrons. We know nitrogen has 5 valence electrons. Then we have 3 oxygens, each with 6 valence electrons. And then because it has a -1 charge, we know it added 1 electron to this ion. So adding all those up, we should have a total of 24 valence electrons. Now I'm going to put my nitrogen in the middle, and I have 3 terminal oxygens. Just remember, when you are using nitrogen, it's in the second period of elements, which means it cannot have an expanded octet. So I'm only going to bond out 4 of nitrogen's valence electrons. So it would give me 1 on each oxygen and then 1 double bonded oxygen. So then I'm going to add in all of my lone pairs. And then I'm going to double check that I have 24 valence electrons. And I do, so let's go ahead and calculate formal charge. Now we know nitrogen is not bonding how it wants to, so let's go ahead and calculate that. Nitrogen has 5 valence electrons minus the 4 bonds gives us a +1 charge on that nitrogen. And we know by now an oxygen with a single bond and 3 valence electrons gives us a negative charge. So we have 2 of those. So overall, one of our positives and one of our negatives cancel out, so this structure only has a total charge of -1, which is what it says at the beginning. So now you can go ahead and do your resonance structure by bopping that pi bond to the other 2 oxygens. All right, so we've already done formal charge a few times in this video already, but if you wanted to actually have some more background information on it, you can go ahead and pause the slide and read through it. All right, so now that we've done a few polyatomic ions, I want you to pause the video and try to do the Lewis structure for phosphate. So for phosphate, it is not in period 2, which means we can have an expanded octet. So I'm going to put phosphorus in the middle, and then I have my 4 oxygen atoms. Phosphorus has 5 valence electrons, so I'm going to bond out all 5 of those electrons. So I have 1, 2, 3, 4, and 5. And then add in my lone pairs. So this oxygen has 2 bonds, so I only need 2 lone pairs. And then these oxygens have 1 bond, so I need 3 lone pairs to satisfy that octet, or 8 electrons. So now my phosphorus atom has a formal charge of 0 because it has 5 valence electrons minus 5 bonds. This oxygen on the right here also has a formal charge of 0, but the 3 oxygens on the left side all have a charge of -1 because they have 6 valence electrons minus the 6 dots minus the 1 line. So each of these have a negative charge, which is where this 3 negative charge comes from on the molecule as a whole. Now, of course, we have 4 oxygen atoms and only 1 double bond. So when we are drawing the resonance, it's going to look like a double bonded oxygen in a different location on each of the 4 resonance structures. And let's do one more example for this lesson, and then we'll be done. So it says possible Lewis electron dot diagrams for SeO2F2 are shown opposite. Which structure, A, B, or C, minimizes the formal charge for each atom in SeO2F2? And then justify your choice. So what I want you to do is pause the video and assign formal charge to all atoms that have it. Now remember, if you get stuck, look for the atoms that are bonding how they are not supposed to. So for example, oxygen is supposed to have 2 bonds, 2 lone pairs. So if it doesn't have that, calculate formal charge. On this first molecule, our fluorines are supposed to bond with 1 bond and 3 lone pairs, and both of them have that. Oxygen is supposed to bond as 2 lone pairs, 2 bonds, and both of them have that. Selenium has 6 valence electrons, so that is not bonding how it's supposed to. However, if we calculated formal charge, 6 valence electrons minus 6 bonds gives that a formal charge of 0. So A is most likely going to be the answer because there is no formal charge on any of the atoms. Then moving over to B, we have an oxygen that is not bonding how it's supposed to. It only has 1 bond. So this oxygen has a negative formal charge. Selenium has a 6 valence electrons and it only has 5 bonds, so it's missing 1. So the selenium has a positive charge. And then going over to option C, we have 2 oxygens that are not bonding how they're supposed to. Each one of these have a negative charge. And then again, selenium has 6 valence electrons minus 4 bonds. That gives us a 2+ charge on that selenium. So technically they all work, meaning they all bounce up to 0 and they have the correct number of total electrons. However, A minimizes formal charge because there is no formal charge on any of the atoms. I hope this video helped. If you have any questions, please do not hesitate to ask. Have a great day. Bye.